Can you hear me?
Yep.
Hello. Today we are going to be talking about scene relighting for video. So what does our work focus on? It focuses on relighting an existing scene for which no ground truth lighting is available. There are other relighting algorithms, but they focus on specific type of scenes like faces. They make use of explicit geometry or landmarks available for known scene. Compared to that, our method has no prior knowledge or assumptions about the scene. Applications include changing lighting in videos that have been already filmed and would be expensive to change lighting by refilming, shadow removal, augmented reality, and 3D compositing. The baseline uses the technique from computer graphics to generate dataset for relit images. They use a network trained to relight images using only the source image and retarget lighting. The network contains exclusive refinement methods for faces, so it does not generalize well to other objects. It also leads to artifacts when the background occupies a significant part of the image. Additionally, flickers are generated when relighting videos. So what is the novelty in our approach? We are proposing a method that generalizes to all scenes and is not bounded by any prior assumptions. We exploit the scene geometry for this and also optimize for video by enforcing consistency between frames and recoloring images. Here is the pipeline for our method. We take an RGB video and generate reflectance in normal images. We warp them to enforce consistency, generate shading for the relit image using target lighting, and then recreate the video. To estimate surface normals, we use a network called RefineNet. You can see the estimated and ground truth normals in this slide. To generate reflectance and shading images, we use an intrinsic image decomposition network called Intrinsic. The reflectance, aka the albedo image, is an image that tends to portray the scene in uniform lighting conditions, which serves useful when applying a target lighting.
In order to relight the objects in our scene, we use the Lambertian shading method from computer graphics. And in the top right here, you can see that the lighting intensity depends only on the surface normal and the direction of the light, so it's completely independent of the camera. This means that if the lights are far enough away from the object, we can pre-compute the lighting intensity as shown on this gray sphere. And by mapping the surface normals to the lighting sphere, we can generate the shading image, which dictates how bright or how dim each pixel in the image is going to be. And we can get the final relit image by multiplying the shading image times the albedo. Next, we tried to optimize for video. We found that the normal estimation wasn't very consistent from frame to frame. So we took 4 different frames and warped them to be in the same perspective before averaging them to get a better estimation. And we also collected some RGB and RGBD videos to test our network on. The depth data was gathered with the Microsoft Kinect sensor, and that gave us ground truth normals to compare against.
So here are some qualitative results. We have 3 images relit with the 7 lighting conditions as shown by the spherical harmonics in the upper right. As you can see, items like the vase in the middle photo and the candle holder on the left pretty clearly demonstrate the change in illumination as the artificial light source is moved around the sphere. For our quantitative results, we use 2 data sets. The first is the multi-pi portrait relighting dataset, which consists entirely of faces and is popular for evaluation among portrait relighting models. Our psi MSE was noticeably higher than that of our baseline and the other portrait relighting models, and we attribute this to the inaccurate facial normal estimations, which is something we'll talk about later. Since we were focusing on relighting for general indoor scenes, we considered this outside the use case of our method. The second dataset we evaluated on was the multi-illumination indoor scene relighting dataset. Here we again calculated a higher error, likely due to the more pronounced effect our model had on the scene than the baseline. However, qualitatively, we found that our model was more effective in the directionality and general appearance of the relit photo. We noticed that the baseline produced a more general filter of the desired lighting, while our approach more clearly incorporated shape. For our video results, we see significantly less flicker than the baseline as the camera turns, as well as clear shading of the surface geometry. And as I mentioned on the last slide, our model doesn't produce as much of a filtered effect as the baseline.
So to better understand our results, we had to look at the limitations of our method. One of the main limitations is that we don't generate shadows for when objects block light sources in our scene. We also don't generate a roughness map, which would allow us to reflect more light off of predicted shiny surfaces and less light off of dull ones. Our albedo generation can also struggle with harsh lighting conditions. The main limitation that we found, however, was in our normal estimation. To test how our algorithm performed with ground truth normals, we used the Azure Connect depth footage we collected before. As you can see in the results below, the ground truth normals created a much smoother and more realistic lighting that outperformed the others in video relighting. To conclude, despite having a higher error than the baseline, our novel method for relighting videos produced less flicker and at a more convincing scene geometry. In order to draw better accuracy conclusions, more dataset benchmarks are needed to compare against in this area of research. Finally, when given ground truth normals, we are able to produce very realistic and accurate results. We believe that given the rapid advances in depth and normal estimation in computer vision, our method will be a competitive one within the next few years.
So why your result is so still flickering? Is that because of albedo estimation is not consistent across time? I mean, it seems like the surface normal you guys regularize such that the temporal coherency is applied, right?
Luis, you want to talk about that? I know you did the
Yeah, so we applied the averaging to both the albedo and the normal. I think this particular video with the connect was, we generated that before we implemented the anti-flicker.
Yeah,
so the previous results with the video, I think, are more accurate.
Yeah, still here, the proposed method, still there's a lot of flickering. I wonder whether your surface normal is estimated correctly, but the albedo is problematic. So there's like three factors, like lighting direction, surface normal, and albedo, right? I wonder what actually messed up.
Yeah, I think the surface normal was the most unstable. So even though we are averaging between frames, that there's still some flicker left in the video. And if we try to average across even more frames, the warping started to become unstable and we would get a trailing effect. So we found that around 4 frames was a good balance.
Okay, I would expect to see like that kind of analysis, like more quantitative analysis on what is weak, what is noisy in the final report.
Okay, yeah, we can do that.
Sounds good.
I have a quick question. So how can you compute the warping field between images?
Sorry, I had to get off mute. So we assume that since it's consecutive frames, the perspective isn't going to be significantly different. So we just use a simple homography to warp to the original frame.
I see. Yeah, that probably will some of the issues that make this thing unreliable, because if you just use homography and if you have a significant translation between frames, the corresponding pixel between multiple frame might be incorrect, and then basically you are averaging the the wrong pixel correspondences.
Yeah, and there's definitely other ways to do the warping function. We found even with the homography, the runtime ended up being significant. So we kind of went with a simple method so that we could run the videos in a reasonable amount of time.
Okay.
Thank you. And move on to team 2.